All right, so we did uh, two parts to problem number 6 in the last video. We didn't finish up actually problem 6 because there's a third part that we didn't hit. So this third part is still an applied situation, but I want you to find two positive real numbers whose product is a maximum and whose sum is 110. So biggest thing about this one is how do we describe those two numbers? What's the general way to describe them? Now, as far as the product is a maximum, you can kind of think of that as the parabola side of this problem. But the first part is really the more important part because this helps us establish what those two numbers are. So, you can kind of set this up a lot of different ways. But if you let x equal the first number, now you got something. Now, a common thing that you could do is to say, okay, well, if x is the first, let me let y equal the second, which is fine for now. But what did we do with it from here? Okay, we got our two numbers, x and y. Well, this is got to be true. The sum has to be equal to 110. So we know that x plus y equals 110. Now, we like to have x's as part of our functions. We don't necessarily want y's in there, but from this we can quickly see that y should be equal to 110 minus x. So now we have our two numbers. So x is the first one, and this 110 minus x is the second one. So now we have our two numbers. Now we can tackle the rest of it. It says whose product is a maximum. So if I were to say that f of x is equal to the product of these two numbers, I would say it's equal to x times 110 minus x. There's my product. Now again, depending on what x and 110 minus x are, you're going to get different products. But we don't care about any product. We care about where that product is a maximum. And if we do a little bit more work to this, we can see that we got 110x minus x squared if we distribute. And we can reconfigure it a little bit more to that. So we do have a parabola. We do have a quadratic function. So, and the other thing we should be able to see from this is that it will have a maximum because the coefficient of our x squared, our a value, is negative. So we should be good to go. So where does the maximum happen in a parabola? Dun, da, da, da. We know it happens at the vertex. So we just need to find the vertex. But because it's not in the right format, let's use that other method to find the vertex, which is based off of the axis of symmetry. So negative b over 2a. b is 110, and a is a negative 1. So 110 over negative 110 over negative 2 better be 55. So 55 is going to be one of our numbers. That's x. X is 55. So now the question is what is y? Well, we can just plug it right back into here. 110 minus 55 is also 55. So the first number is 55, and the second number is 55. When we multiply those two numbers, we will get a maximum product from that. So very, very quick once you have a function, but you had to know how to set it up. So this was the setup. Get your values for your two numbers, and then you can multiply them to get your function. Okay, the last application of this is looking at, and we already had an example similar, but this gets into the finer details. The height of a projected object. So if air resistance is neglected, the height s in feet of an object projected directly upwards from an initial height s sub 0 feet with an initial velocity of v sub 0 feet per second is s of t equals negative 16t squared plus v sub 0 t plus s sub 0, where t is the number of seconds after the object is projected. So again, you're just throwing it up in the air. So let's look at a specific application. We have a rock is launched upwards from ground level with an initial velocity of 90 feet per second. Let t represent the amount of time elapsed after it is launched. Okay, so explain why t cannot be a negative number in this situation. Well, t is the number of seconds after the object is projected. Can t be negative if it's time? No. So time cannot be negative. We're not doing time travel. Okay. B, explain why s sub 0 equals 0 in this case. What was s sub 0 again? From an initial height s sub 0 feet. So why is s sub 0? Why is the initial height 0? A rock is launched from ground level. If it's on the ground, so basically they're creeping their hand underneath it or whatever you're using to fling it, but your hand is on the ground, it's touching the ground. And so you're just underneath it and then you heaved it up. So rock is initially on the ground. Okay. So let's see. Give the function s that describes the height of the rock as a function of t. All right, so we know s sub 0 is 0, so that takes care of that piece. So now the other question is what is v sub 0? And we got it right here. Initial velocity of 90 feet per second. So we should be good to say s of t equals negative 16t squared plus 90t, and then plus s sub 0, which is 0, so we don't even need anything else. So that should be our function. Now the question D, how high will the rock be 1.5 seconds after it is launched? Well, so we want to replace t with 1.5. So what is that going to give us? Well, again, use your calculator, but 1.5 squared is 2.25. So I'm thinking that is what, negative 36 for that. And then 1.5 times that, so that's what, 135. So we can do that pretty quick and we get 99. So after 1.5 seconds, the rock is 99 feet off the ground. That's pretty wicked, right? Okay. Now, if I made a mistake here, obviously just let me know, but I'm pretty sure I did it right. Okay. So it says what is the maximum height attained by the rock? After how many seconds will this happen? Determine the answer analytically and graphically. So personally, if you can do it analytically, then the graphically should be pretty easy to do as well. But let's do it analytically. So how do we determine the maximum height of a parabola? Well, if it's not in the right format, then we got to use the axis of symmetry. So negative b over 2a, so 90 is b, so we want a negative 90 over 2 times our a, which is negative 16. So the negatives will cancel, so 90 over 32, and I'm going to be lazy and use my calculator. So 90 divided by 32 equals 2.8125. That can't be right. I guess it was. 2.8125 seconds. All right, so that is the time it takes to get to that maximum height. But what is the maximum height? Well, we have to plug that in. So S of 2.8125 equals, so we got to plug that all in. Oh boy. So this is going to be a fun one. Let's maybe get our graphing calculator. That might be a little bit easier to see it. So let's turn this baby on. All right. Hopefully you can see that. So we're going to have a negative 16 times 2.8125, and we need to square it. And then we want to add 90 times 2.8125. Let's see what we get. So 126 and change. Now obviously you want to round these if you need to. So in this case, if you wanted to go to the nearest tenth, it doesn't really say what to round it to, but usually the nearest tenth is not a bad place value to round to. So 126.6 feet roughly is how high that's going to go. So we have the time it takes and the height it gets to. So last question. After how many seconds will the rock hit the ground? Determine the answer graphically. Well, again, graphically or analytically is fair game in my book. So, what do you think for this one? How are we going to know when it hits the ground? What do we know about the height when it hits the ground? Well, the height, if it's on the ground, the height is 0. So we basically just need to know when our function is equal to 0. If we can find out when it's equal to 0, that's when it should be on the ground. So we can do a little bit of factoring here. We can factor the t out. Well, we got the one case of t equals 0, which is duh. We don't care about that one. But when negative 16t plus 90 is equal to 0, 90 over 16, and just to get a nicer answer, looks like 5.625. So 5.625 seconds. All right, let me get my head out of the way. Either that or I'll just shift it up a little bit. So that should be the answer for how long it takes to hit the ground. So the big thing to take away from this one is that you don't always have nice answers. So usually you will, but not always. There will be sometimes these application problems can be a little bit yucky, but the concept should still hold. That's the important thing. So, alrighty, so that wraps up this video, and we'll be in the next section in the next one. So see you soon.